Okay, here we are. This is the title is the same as last week. The content is radically different, both in approach and in substance. Okay, so whereas last week we were really looking at some technical details on how to view conjugate poles and how you can look at conjugacy both in the overdamped and the underdamped case, so both when you're purely discounting or when there is a possible business cycle going on. Now I'm going to take a completely different tack and start with some with the economic tradition on business cycles. Okay, and then there'll probably most likely will be a third lecture where I try to tie it all together. Okay. So that's what we're going to do. And if you look up business cycles in something like Wikipedia, or this is, I think, from the Encyclopedia Britannica, that's not a bad resource. You're not going to find the latest of the latest, but you're going to find things that, like the way an economist might look at this. This is a picture that I just snagged from the Britannica. So here, this is for an economist, a clear-cut case of a business cycle, all right? So he talks about this, and he sees a cycle here, boom, boom, boom. And then another economist might go along and say, well, that's not a cycle at all. And then they suggest not to call it a cycle, but to call it a fluctuation, since one guy cannot see a cycle. Okay, and they have discussions like that. Very, very unclear on what's going on. Another thing that's unclear to them is whether the cycles are occurring by themselves, endogenously they would say, or whether they need something from outside telling them what to do, right? So this was just a download of yesterday, but they started 1790, so that was before I was born, can you believe it? And the end of 1940, which happens also to be before I was born. So it's quite old data, but you can see a huge gap here, for instance, in Germany.
And what's on the y-axis here?
They never say. You have no idea.
But this is GDP, probably.
Probably output, they would say, or economic activity, or GDP, right? Huh? Sometimes they'll plot the price level, huh? But they'll have a vague kind of thing. And they'll call this an indicator of economic activity. So they may make some measurements for demand, or some proxy for actual output. They don't quite know how to measure it, right? So that's a good question. What's on there? We kind of don't know, and they don't know either. Huh? But they try to do their best. Let's not be too critical. Huh? And the other thing you may notice. So just to come back to where it comes from, obviously, I mean, where do you think this big gap comes from in 1918 or something? Yeah, the World War I, right? Huh? Hugely devastating for Germany. Everything is, and they have to make huge repayments. They never really come back, right? Huh? So huge spending leading up to the war, and then...
Isn't this because they devalued the currency?
No, that was later.
Well, that's another...
Because the other spike is the Great Depression, right? In the United States and Great Britain. That's in the 20... maybe it's...
No.
Yeah.
This is really so they had a lot of investments for the war.
Yeah.
And they fought it.
Okay, right.
And then the whole economy crashes and it seems to stabilize at some level. This huge expansion here, there's a huge expansion in Germany occurring starting around here. It should be. So... Because here is German unification, okay, the Franco-Prussian War. So before that, you guys weren't born then, neither was I, but Germany was small states. In the Franco-Prussian War, they united and they knocked down all the internal tariffs. So now all of a sudden you can trade. And then around this time here, in the late 1800s, they start building railroads in between all these different German states. And the railroads really boost them up. France, United States also starts building railroads. Great Britain was a little bit earlier in building railroads. That was in the time the Great Connector. Okay. Later, Germany uses these railroads to move their troops. right? That was the original intent for those railroads, not commerce, but to move the troops, because they have to fight a war on two fronts. Because the Roman Empire did the same. They built the Roman roads to move the legions, and then they figured out that if you have roads, then trade starts happening along the Roman road because they are safe and they're paved, and then you get a huge boost in economic activity that actually makes the Roman Empire very much stable. Huh? So, but then you see others that are just kind of going up. There are all kinds of cycles in here. So they'll have discussions about it. The other thing that strikes you is that the thing seems to be stable. So that's, of course, cannot be true if this is GDP, because GDP is rising, right? Yeah? So they must have detrended it. So economists...
On the left it says something like percentage change, so can it just be the... goes up and...
Yeah, but even that is growing because you get exponential growth, right?
Well, if GDP is going up,
Right.
it would mean that the average of the year growth rate is not zero, but because it will go...
Yeah, but I mean, suppose this goes up, right? Then the, what is the percentage? Is the
If I work because funding, that's where it comes from.
right.
So now if you take a log derivative, then you can...
You have to take the log derivative, and then you get the exponential out of there.
Yeah,
Huh?
exactly, yeah. But then
Yeah.
the log derivative is also the percentage because you divide by the...
Yeah.
the
Yeah, because you do the integral of dx over x, right? Huh?
something like that.
And then you get the log, huh?
Yeah.
So this is the growth divided by the relative growth. Huh? That's the percentage change. Yeah, so maybe that's it. But that's one way of detrending it, is just looking at this thing, right? You just look at the log, so the log, you know, so you'll get something else. But you'll see, I'm not sure how they did this. I just kind of copied it, and we can talk about exactly how they do it. They'll do it in many other ways. So many times you'll see an effort first to detrend the data and then to look at the cycle, okay? Now, let's try to, what I want to do with this lecture kind of make sense of these kind of pictures and the way they would reason about it. So what I wanted to do first is talk about the trending, the detrending, okay? So there are really two things going on. There's a feeling, there's a trend, you know, so that's a growth trend or a contraction trend. And then on the trend superimposed are nevertheless cycles. So now let's look at our second order system. And here is like, here you see, here's the time function of such a system. And if you take the Laplace transform, this is what you get, okay? Now, if you look at this, you guys all recognize this, right? So this is your damping factor, is your natural frequency. So this is something called the damping rate. And this thing right here is something called the damped natural frequency. So the thing is going with a damped natural frequency, and at the same time it's modulated the signal by being damped out. So if you make a plus sign here, it will just kind of jump up. I think in the Laplace domain, yeah, I did it here. So I stole somebody's picture here, where you just kind of, for a second order system, kind of show how these things go. This is, of course, a first order system, right? Huh? Okay. So the idea, if you go back to systems engineering, then this idea of a trend, which is this part, and a cycle is built in a second order system. Okay? Let's read it off. So you take the second order system, and it's pretty clear that if you look at this ratio, you take the square root, you get this omega n variable, the natural frequency. If you divide the mass by this, then you get this gamma, and if you set that equal, blah, 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 blah. You know, you guys all know this, right? Economists do not know this. You guys should know this. So you can see that a system like this has all the right characteristics. Now, and not for growth, but for shrinkage, okay? So let's just keep ourselves to a contraction. So why would it have this? All right. Well, what's happening, of course, here is some demand, right, or supply. Here is some storage in this spring, huh? And these together, they cause the oscillations, right? So there's demand. So you start buying, you put it in storage, you go, oh, I got way too much. And you go like, okay, let's get rid of it. And then you buy again, and then you got too little. And then you start buying, and then you have too much. And then you just keep cycling up and down, all right? So this is some storage and demand. If you just have demand, nothing is going to happen. The thing is just you're going to keep demanding, and you're just in partial equilibrium. As soon as you have storage, you know, you have some abundance, and you go, wow, man, I got way too much, and then you try to get rid of it. You give some away, or I don't know what you do. You sell it, right? And then this damper, that makes care of other things, just these commodities or whatever it is, or maybe it's capital equipment getting lost, so maybe this is depreciation, or it's just like spoilage, or you're consuming it, I don't really know, right? And with this kind of system, you'll see that you have some fees you're paying here, you'll have some convenience there, you'll have the regular force of demand there, and they all work together to provide you this thing. And you don't have to fit any data. As long as you know what these parameters are of your storage rates and your this, you can just derive what this should be. So, you know, you see there's a really nice fit to this idea of damping and trend and a second order system. Okay? You look at the value of such a stream, you know, so we look at it in the discount cycle, and there we go, right? So we got these conjugate poles going on, and depending a little bit on zeta, there'll be complex conjugate or these kind of hyperbolic conjugate ones that we talked about, okay? So we're doing pretty good. Here's the bond graph. You know, here you see the I element for the demand, the C element for the storage, for the R element that's just dissipating your surplus. So the fit is phenomenal. You can, the detrending, you know, you do via this, the damping ratio will, you first have the natural frequency. This is kind of they won't say frequency, they will say a cycle. You know, they don't like the word frequency, okay? So they'll talk about a natural cycle, but they don't have a really good definition. We'll just use this, right? Then you will see the actual cycle. There must be the damp, so it's not really going at that unless there is damping. And of course, our old discount rate just shows up here, okay? So if we forget about all these things here, then the thing is just going down. If this thing is just 1, then it just goes down, discount rate, okay? All right, so this puts us in good shape. So now, this is the first thing that I just want to get done with, is that we can detrend this data. And this is how we do it. Now, an economist will not do that, actually, surprisingly. They will think of the trend as very, very low frequencies, okay? So they will only look at frequencies then, and they'll say the trend is a frequency right here. Huh? That must be a pair then. Somewhere right here, very, very low, not 0. Huh? Now, we don't want to do that. That's not right, you know, because it's not a trend. You know, it's just, you know, a trend would be something like this, and this thing is doing, what is it doing, right? It's going like this, you know, huh? I don't know, huh? So the derivative is wrong. Everything is wrong about this thing, okay? The other thing is wrong. It's going to take a long time, but it will go down. It's still a frequency, all right? Now, if this thing is infinitely long, we'll get hyperbolic corrections to the overall trend, okay? That's what you get when you have very, very large damping factors, okay? So, but the trend is this particular value, right? So that's a slightly different approach we take, and I think it's important. So can really separate that, and you will see later, this is where the Laplace transform shines, you know, because it has the frequency will have a real component where you can put the discount rate. So I'm going to keep this on the discount rate. And it has these imaginary components where you can see the deviations from the regular discount rates implied by the effects of having demand and storage acting simultaneously on the thing. Okay? And that's why in engineering, a lot of times overdamped systems are treated, and also critically damped systems are having real eigenvalues. That's why we did a lot of work last time to show that that's not really the case. The real value is just the is the discount rate, and then there are these hyperbolic values, this j square being 1, that makes 2 modifications of that. Okay? So that's the first thing we do. Everybody cool with this? Any questions? Now let's go look at just cycles. So let's detrend our data. So we threw out, just think this away here, and we're just dealing with this, some sinusoid going up now, or cosine, all right? Huh? Now they have, if you look it up, they'll have a whole list of cycles that they have inventorized, and they have long discussions which ones are real. If they talk about the cycle, it's always this one. And then you have...
So it's the inverse of the what they're talking about.
Yes, it's the period. Yes, yes, you're right. So a cycle can be anything, right? You can measure it with a frequency or a period. And here, this is the period, right? Huh? Yeah. Yeah, they don't want to do 1 divided by 2-5 or something, right? It's all, I mean, these are important questions because it's all fuzzy. Yeah, they don't really have this really very accurate sense of frequency and Laplace transform and complex numbers that we have. They have to do it all without complex numbers. Economists don't learn complex numbers in their undergrad curriculum. So they'll call these things nonlinear systems. And I've been to an economist and he says, look, it's nonlinear. Look, it's a sinusoid, right? I said, no, that's a linear system. And I says, no, it's not linear. Look, here's a line. It's not a line, right? Huh? So, I mean, why is this a linear system? Does anybody know?
Linear in the angle.
Yeah, it's only in complex numbers it's linear, right? You just have complex numbers, you have this equation, a linear equation, right? The real numbers, the thing won't be linear. You'll have all kinds of mess around. That's exactly right. So you have to expand your number system so that you get rotations as linear operators, which is all the work we've done last week, to realize that this is a linear system. It's just linear as long as you have complex numbers. Now, if the thing is bigger and you have more stuff going on, it's going to be linear in some bigger domain. So you have a matrix exponential. So you plop a big matrix in your you write something like this. Huh? What do they do? Did they put a minus sign here? I don't know.
It's like
What?
It's like that.
Yeah. Yeah. I mean, what is this number, right? Like, oh, don't worry about it. Huh? I mean, here's a Taylor series and it will converge and blah, 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 you know. But really, you see that linearity is always this, you know. So you take a derivative and the A comes down and you just make sure that everything stays nice and linear. If you need complex numbers or higher, those are called Lie groups in general, but we'll try to avoid that theory and deal with complex numbers. And that's why I introduced these double numbers, just because you don't want to get into Lie group theory unless that's your focus. Okay? But to understand it, it's not necessary. So there are these cycles. You can read a lot about it, you know. And then here's a picture that they'll have with it, right? So again, very unclear what's on this axis, right? This axis will be time, huh? But they've color-coded it, and they'll have an expansion. So this must be some measure of economic activity, right? Huh? Maybe kinetic energy, right? Yeah? So that will be economic activity, the surplus that's in there, right? Huh? So maybe the kinetic energy goes up. Here the kinetic energy is maximal. Here the kinetic energy goes down, and here it's, I don't know, it's negative. It's in the other, something like that. We'll find out what it is. I want to look at these rotations in the phase plane and match these things with the harmonic oscillator. Okay? This is called the jugular cycle, and they have this thing. You can read up about it. You see they expand, so economic activity goes up, there's a boom period, then comes the recession, then the depression. They have long discussions whether these things are necessary or not. Some economists will claim it's not. And they'll say that the mandate of the ECB or the Federal Reserve is to get rid of this stuff and to make everything look like this. Okay? There's others that say, no, this is the only way it can work, and you need to have excesses in this, and this is the only way the system can go into equilibrium. Both parties have something to say. In macroeconomics, you have a lot of people with power who say they're not necessary, but in business, there seems to be a consensus that you need inventories to go fluctuate in order to, to do business. There is no dealer. There's been attempts, so they have this thing called just-in-time delivery. So Toyota was very good at that. So a lot of old businesses, they had enormous amount of raw materials or parts they would order. So Ford Motor Company would order all these parts, and they would have a big assembly line, and the assembly line would be taking a generator or a wheel and putting it on, and a nut. So they would order huge warehouses and then push it through. And then somebody else would be keeping, make another big order, and a big truck would come in the warehouse, and they'll keep the line running all the time. And then Toyota decided to go to very small storage facilities. They call it just-in-time, JIT. You may have heard of it. It's a little bit outdated now. It's a Toyota manufacturing system. And they had an idea of very small inventories, because the inventories were, I used to teach a course of this in Berkeley. That's why I know quite a bit about it. So the inventories would be quite low, and they would save a lot because they didn't have all the money tied up in inventory. But then all the American and European manufacturers would say, yeah, but then the line will go down as soon as something happens, and this and that, and there was no delivery. But they said no, because there is pressure on the system, we are keeping it going. And the Japanese, of course, are notoriously very precise about this thing, so they were able to do it. The Americans and also the Europeans, the Germans in particular, were able to get it down, but they don't have the level of precision. They never were able to pull it totally off, And secondly, the Toyota still had inventories. Okay? So you can play around with that, and then you get very different inventory cycles. Okay. Then of course now we have currency traders, and they'll trade in, or not currency traders on the stock market. They are high frequency traders. So I've been on the stock market myself, and after teaching these courses, by the way. And there, you see on the stock market, you have something called a dealer, and that's distinct from a broker. So a broker doesn't have his own stock. He doesn't have his own inventory. It's like a real estate broker. He just makes the deal. But he doesn't actually your real estate broker won't first buy the house, then keep it, and then wait for a customer. He will just sit around, make the deal, and let it go through. So he acts like a resistor, okay? But a dealer is quite different. So a second-hand car dealer, he will buy used cars, put them on his lot, and then wait for you to show up and then buy it, okay? Even a new car dealer would do that. Although they typically have deals with the manufacturer, they give him free cars, so he doesn't really have to worry too much about what's on his lot. Okay, but a normal, that's a dealer. And the same is on the stock market. So there are dealers on the New York Stock Exchange, and they are on the NASDAQ. You have this thing like a market maker. These are just guys, the dealers, they are hired by the exchange. Well, no, they're contracted out by the exchange. Market makers is kind of a free thing, and you just have to hold your own inventory of stock, and then you buy low, and you try to sell high, and you just sit and wiggle in between. So you have your own inventory, so you have exposure, okay? So you watch these guys, and they've been pushing this out to a microsecond. I watched a guy, or I looked at the guy on when I was waiting for a flight that would never leave, on the airport, and this gentleman, you could see what he was doing. A flight would come in, say from the United States to Holland. Everybody was, this was in the olden days, everybody would change the currency, right? And then 2 hours later, another flight would go the other way. You'll see, and then he was 2 hours or 6 hours something like that, right? And then he would sell all the dollars again and then buy euros, and then this way his inventory would go up and down of dollars, all right? I think he was on something like a 6-hour cycle. A lot of people are on 6 hours, so it's kind of interesting because that's 4 times, so you can boom, 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 you get 24 hours. It's exactly in a day, or 2 in a day, because they work 12 hours, or 2 times 4, or something like that, right? Okay. You have these seasonal cycles, and they're associated, you know, with our life. You know, it gets cold, you do different things or something. We'll harvest. We'll see that later. And a lot of business have an accounting cycle. You know, they just make up the books, and then you got to pay your taxes. So they'll sell a lot of stock in order to not make a capital gain tax. And you see all kinds of movements in the stock exchange, and here in the Netherlands too, in order to avoid certain taxes on capital, they liquidate certain positions, so they're on a yearly cycle often. Okay. So the cycles are just kind of built into business. These are more business cycles. They can get quite small, you know. These are also periods, of course. But if you talk to economists, they don't really pay much attention to this. I think we should, because we are a little, you know, when I say economic engineering, I also mean business and finance, of course, right? Economic is more the fact that we look at economic laws, right? Not really the fact that we don't do business. Here is a famous, I took this graph because it's a lead into the next slide. This is called the Kondratiev cycle. It was done by a Soviet economist. A lot of Soviet economists have contributed to this. Look at these names. This is a Frenchman, but Kichin, Kuznets, Kondratiev. So they had a lot of interest in this under the Soviet system because it was very much a controlled economy. So they studied this, how they could influence the cycle and how they could like have these 5-year plans and all these things. So Mr. Kondratiev, they later all went to the United States when the Soviet system collapsed. This one, he has a huge cycle. So this is a famous one, right? So the idea is that technological innovations drive businesses. So you have big inventions, you know, and that changes everything. So you have all these theories, but here's the one that, so you invent the steam engine. So you can now make cotton and clothing by engine rather than people doing it at home. And boom, you get a huge one, and then a contraction. And then the railways come, boom, all right? And then they do all this electrical engineering stuff, huh? And then the automobile comes, and now we're doing this one, so they dotted it, you know. That's you guys who are doing that. So the idea is that it comes from there. Okay? So very large field. What I feel at the first instance is, I think, a little bit confusing for us is something that I put on the next slide. The difference between endogenous and exogenous. I see there's a little bit of a busy slide, but let me first go back here. Now look at this Kondratiev cycle. Compare that to a regular inventory cycle. You know, inventory cycle is just the way you do business. You know, you need that, you do that, and you know, no events are needed. You know, this is the minimum you can do. You know, given the constraints on your road network and whatever, right? So, but this thing has a different feel. It feels that there's something from the outside is making this invention, and you're counting on this, you know, now, and that will give it a portion, then start oscillating. Okay, so it's so these things are called by economists. They have a long debate on whether the cause is exogenous, like you would have here. So from without the system, the economy is just there, and now boom comes this new invention. Okay. Or endogenous, what this is. meaning it's within the system. It's just kind of, okay, it's there. And they can't decide which is which, right? Are cycles endogenous? Are they exogenous? Some claim all are endogenous, some are all exogenous, you know. There was a huge discussion that traditionally all economists thought it was endogenous, okay? So that means that the economy should be left at its own devices. You just see what happens, and everything is in the system, and it's just going along, okay? This is also associated with laissez-faire type of policies. And then comes along this guy Keynes, and he says no, because that was in a period of stagflation, so they let the economy go, and then it wasn't doing anything, and then he says, okay, we have underconsumption, and then he came with this idea that the government had an important role to do. He could intervene in the economy and adjust the business cycle, okay? There's an interventionist approach, and it comes from the outside. So the government is here an agency from the outside that intervenes, and it's its duty to intervene. And they even rewrote the charters for the Federal Reserve, and ECB is from much later, so that the government would have the power to do that. Okay. Now, how would you place that within this whole discussion? So there's a nasty discussion between these neoclassical guys and these Keynesian guys. I mean, they really are at each other's throats, right? And it has a political dimension because the Keynesians tend to, there's more left-wing or politicians tend to rely on these type of things because they favor bigger government, and more right-wing politicians will favor this neoclassical theory, right? So everybody favors the theory that fits their agenda. So it's not something that looks like it's about to be resolved as if anybody would like to resolve it. You know, I don't think anybody wants to resolve it. So this is just a way we balance it out. But now let's not worry about that. Let's see, how would we look at it from a systems and controls perspective? Okay. And this is, of course, a big brushstroke, but I think it's precisely the spirit is precisely the difference between systems and controls, okay? So there is when you have a system, you think of it and divided out of two parts. One is just the system itself, and the second one is, you can put the controller here, I guess, but I'll just put it here, the controller, right? Yeah? And they're different systems. And this controller has got some force at which it's pushing the system. And somehow this controller gets some money. I don't know where it gets it from, but that's the feeling we have, okay? And we'll study systems in two ways. We'll look at this as a sort of autonomous thing. So you just take the initial condition and see what the thing does, okay? Right, so it's a little bit, there are several theorems, fundamental theorems of welfare where economies do that. They say, okay, but they can see what it does when it comes to equilibrium. And the other is to say, no, let's see what it will do under certain types of interventions. You know, so we do this, we change that. The Federal Reserve will adjust interest rates and do this, okay? So then you start making this distinction between a system and a control. Now, this can be, you can make this as specific as you want. I mean, I just go back to my second order system here, and all I did was add this force, this force that is pushing it. And it may be pushing it at some, now AC current there with frequency omega. Well, omega doesn't need to have anything to do with any omega n or d or r or whatever the internal characteristics of the system are, okay? And in the bond graph, you would add this thing, right?
Causality bar should be.
Oh, yeah, shoot. I tried to get this bar the other way, and then it flipped that one. Huh? Thank you. Huh? I had it right, but I had this thing pointing the wrong way. And then the software that I use screwed it up last minute. It's just to give you an excuse why I'm not as silly as
Yeah, I know,
a stupid one. But thank you, right? I find
Maybe
it
it's
super-
just a screen that.
yeah. Maybe it's just your eyes, right? Yes.
And so what's the economic interpretation of this raw input?
Well, that's just the intervention, right? Huh? This is what the so suppose your controller is the Federal Reserve or the ECB, and you have an economy, right? It's just changing something, say an interest rate or something, huh? And that will be the interpretation. Okay, but the government may change tax rates, right? So it's just taxing you, just changing something, right? Or drawing energy out of it, huh? Or you may have in a business setting, you may have your business and you just kind of let it go and see how it works on its own without any management. Or you get management who has some investment from this, who is there to steer this thing and say, all right, we buy this, okay, we'll start reducing this price, and those will be the, okay? So, see, from a business perspective, it's pretty clear that you're going to have both. You know, there is something at which the system says like this, and another one where somebody's trying to intervene and move it to where it should be, you know? Although they never take this explicit difference. They never make the thing explicit. But when economists model an economy, they just throw everything together, right? So they'll have these models, you know, and then they'll have the government here, and they'll have consumers there, and they'll have the banking system there, and then they'll have the producers there, and they say, okay, I'm going to make a model of this whole thing, right? So they're just going to look where the closed loop poles are, right? But they won't take the perspective that one of these is a controller, and this is the system, I don't know, right? And that you have this interaction, and this is just controlling that one, right? You see? Because even if you close this system, there may be China here or another country trying to mess with you, right? So you can think of that as another system or as a controller, right? It's just a different perspective. And my feeling is that, especially in economics, this is where this discussion comes from. Like, are these cycles, are they due to you know, are they exogenous or endogenous? Well, this force here, this effort here, is it endogenous or exogenous? Well, it's an effort source, so it's endogenous, right? I'm thinking of it like that, right? Huh? Okay. So where do they come from? Anywhere you want, really, huh? What I want to achieve here is to see, like, okay, we're not going to solve this confusion, but it's from systems and controls guys, it's just part of the way you would think about it, okay? And I think a lot of you, I see a rumor going up and down with his head, this was kind of a major kind of break in the way you model this business. Okay, what is the controller here and what is the system? And the system is autonomous. So all you need is a bunch of initial conditions and then you go boom, and then you'll see what it does, all right? Huh? But when you start putting a controller, you have a management and they're steering this, well, then you have to close the loop, right? And then you have to recalculate where the poles are, right? So you'll get all kinds of different discount rates, and you know, you never know where they're going to end up, right? And you get different cycles. And they're going to be endogenous, if you look at it as the entire system, but now from the perspective of the original system, they're going to be exogenous and, all right? So that's what this is supposed to, this is what this is supposed to say. Like, we had our old system that we started off with as just totally autonomous, or this is just a homogeneous response. All I did was add this guy here, right? And now I can look at, say, the Bode plot, right? And now what am I going to see? Am I going to see the natural frequency like I would have with a regular oscillator? Certainly not. Right? I'm actually going to see this forcing frequency, at least in the steady state. In the transient, I may get, you know, something nasty, but, well, it's not going to be nasty. You can calculate what it is. It's going to be some combination. Huh? Then in the steady state, this thing will hold. And then in the steady state, you can see what happens. You can look at, well, this will be the resonance frequency, right? What is that? Omega n times 1 minus 2 sigma square, something like that, right? Yeah? Huh?
Without the 2.
No, that's the resonance frequency,
Oh,
right?
sorry.
And I think that's the peak. I think there's a 2 because isn't the peak at 1 divided by square root of 2, which is 0.7, something like that, right? You know, these Bodhi guys, when they do that, they'll go like, okay, this is the point where you don't see a bump anymore. You guys remember that? Huh? Or not? Huh? No, you can say no. Huh?
I don't see the relation with. Okay, so obviously.
Yeah, so I think this frequency here is called the resonance frequency.
Yeah, that's true.
And that resonance frequency, the first asymptote that doesn't show a bump is at where sigma is equal to that. Huh?
Oh,
Right? Huh? And that is, you know, not where omega d is 0, right? Huh? So it's slightly off, huh? I think. It's not really important. Huh? But the point is, all of a sudden you have these, I mean, these are all endogenous things, you know, whatever it is, right? These are various endogenous things that you can calculate from the natural frequency and this damping ratio, right? But this omega, you know, you look at how much you have between omega and omega n, and that thing is, that omega, that's this one, right? So you don't have to be oscillating. You can be oscillating right here, and it's just letting everything through. A nice low frequency, or really high, it's letting nothing through, okay? So the exogenous frequency will always win out here, but in the transient, you'll see a lot of the endogenous ones show up. But then if you let the system go, it's going to go and continue on its endogenous stuff, right? Its own natural frequency rather than the forcing frequency. Okay, there's a lot of details here where what this exactly is. But what I kind of want to do is make a distinction between these things, right? And this one, right? The forcing frequency. Okay. Now this is just an important perspective when you start looking at these economic applications. So when we call it forced, or when it's a controller that's doing it, you know, huh? They would call it exogenous, and inversely, when they will say endogenous, they'll start looking at all these things, right? Descriptions of the system itself that you can get from the poles. Okay? So again, this is not a, you know, you've all seen this, and you all have forgotten it, and then seen it again, and forgotten again, so have I don't really know. But the point is more, the message is here not for us to get this exactly right, or for me then, but to see that I wanted to get the broad brushstrokes down here with this lecture. You know, how all these concepts like forced and natural, and you know, even the distinction between system and controls itself falls within these ways economists are talking. They just use different words, and they may get confused at points where we say, well, this is just the point, you know. Of course you're going to make that distinction, right? This is what we do every day. We just didn't realize that I could apply it to business cycles. But when you start reading them, you get so confused, you have no idea what he's talking about, right? Okay? So, you cool? Let's see, what's our next topic? How many slides do I have? You know, I want to, let me finish this slide, we'll take a break. And then the other ones, they are of a little different flavor, where I really want to go through, you know, now some specific examples in the phase plane, you know, now what this thing is doing, okay? So let's just wrap up the economic stuff, and then we'll spend the rest of the lecture to the analysis and the phase diagram, how we can wrap these things around a circle, right? So economics, just to have all kinds of theories of why cycles come. So one is an agricultural theory that says it's tied to the harvest. Now again, what is this harvest? Is this just something endogenous because people like to eat different things in the winter and the summer, or is it tied to something exogenous where you see production as something out of the system and you just see the consumer is reacting? You don't really know, but you've got to model it, right? There's no point discussing whether it's one or the other. You have to define your system and then say, okay, this is how people are, right? Huh? And then you say, all right, but this is what they can buy. Maybe they can only buy mangoes, you know, because they live in Suriname. Or maybe they can only buy beetroots because they live in the Netherlands.
Yeah, so it could even be that you have a time varying system.
Yeah.
That because you have the harvest cycles, that for example, this elasticity of supply for some goods changes over the year.
Definitely, yeah, definitely, yeah. This is just a list. You go through it. Yeah, I mean, this one can also is psychological. So there's this thing that they have. You've looked at that also in markets. It's called follow the crowd. When one guy is wearing this jacket, everybody else wants to wear the jacket. Some influencer or something. So you start, and then everybody piles on, right? And then at a certain point, everybody got exhausted because they all have this jacket or this pair of pants, right, or this particular stock. And then the thing has to go down, right? So the question is, so they will call this psychological. You know, that doesn't do you much good as an engineer. You just got to look at it quite different. You got to say, well, there was a shortage of this particular types of pants, and they came into fashion. So all of a sudden, there's demand for it that may not have been there, or maybe it was. They just never had the connection. Who cares? But then all of a sudden, you're full, and then you got to do something with it, right? And then I think Koen has a nice application where you can have a derivative controller, right? Where you model these technical traders. So what these technical traders on the stock market do, they try to buy before somebody else buys. So this is a little bit different than your regular question of demand. You know, normally you buy apples because you want to eat apples. You know, you're not going to go to Albert Heijn and buy an apple because somebody else. You want to be ahead of somebody else buying this apple just for the kicks of it. You know, but strangely enough, on the stock market, this does happen. And
also in retail, we have limited.
Yeah, for example, I had to buy my PlayStation at a scalper.
You had to buy it at a scalper?
Black Friday sales, stuff like that.
Yeah, but that's a black market then, right?
No, Black Friday. That's the.
No, but what you did, this is the black market, right? So it's still a market. But these guys, they guess what the market is going to be, price going to be, and then they buy before that.
But it's actually the same thing because they know that there's a really huge demand for it.
But it's not the black market. You can just do it. It's just legal. Yeah, it's just the motivation seems a little weird.
Yeah, so what I did is, so the guys that sold it to me, it's not illegal either. They just bought something that they know has a huge demand. There's nothing illegal about selling something to someone.
That's right. Yeah, that's true. From that perspective, because he has risk too, it may go the other way, right? Yeah, no, that's right. That's right. So, but one of the things Koen did was make a derivative controller, I believe, to get these guys right. So they kind of are, you know how a derivative controller would kind of anticipate the next little event? So that's what these guys are, right? So you're going to, these psychological theories, be a little bit careful. You know, you don't say, hey, I have a psychological cycle there. Just look at what's going on and then try to find. Now, of course, if you have a big derivative controller, you're going to see quite a bit of volatility in your data, right? I mean, sure, it's not going to damp anything out. So that's a good idea. You know, that's a good idea to place something like that in controls. Political. So taxes, restrictions, so they increase taxes or there are input restrictions. So what is that? Well, what kind of tax you can, maybe it's a resistor, right? You just get some stuff out of there, right? So you change the resistance. So you're going to change this zeta, right? your damping factor. If you change the damping factor, you're going to change your damp natural frequency. So that will definitely cause now some cycle. We relate it to a cycle, constraints too, because if you make some input restriction, the thing will have to bounce off, and maybe you'll get another cycle there. Okay. See, technological innovation. Yeah, sure. You have two things that are not in contact. All of a sudden, they are in contact through this, or costs are lowered. So you change the parameter of the system. You may introduce poles, zeros, or reduce them. Of course, you're going to have a cycle associated with those things. You're going to see stuff. Okay. And then you have these demographics. This is a good one, underconsumption. This was Keynes's theory, and we're going to talk more about that after the break. That the cause of the great malaise was that there was not enough consumption going on. So what he suggested, and this is what Biden is doing now, and is to give everybody a huge check so they could start buying stuff. And then they will just buy all these television sets, and I don't know what they will buy. And then all of a sudden, these factories will have to put out these television sets, and they will hire the same people who blah, 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 called the multiplier. And then you have others who advocate for monetary things. I think especially Friedman, who says that everything is a monetary phenomenon. So you just expand the credit through the banking system, the amount of credit people can get. So you don't give them money, you just loosen up credit. And then you can get, these are the ones I want to talk a little bit about. And a couple of others that I don't, inventories, we'll see. Okay. And then the other thing they talk about is leading and lagging indicators. That's a very confusing thing. But you can see that business orders, they're considered a leading indicator, right? So you see orders coming in the business, and then you say, all right, that's a leading indicator, right? So what will happen is that prices will follow later. What would you say as an engineer? Well, these orders, it's like you don't have enough storage, so your capacitor or your C element is kind of, empty or full, depending on how you look at it. So that's going to have a convenience, which is a force, that's going to push a price, but there's going to be a phase delay, right? So you get these phase delays, so you have leading and lag, And they, of course, they don't talk about phase delays because they don't have complex numbers, right? So different other ones. Consumer demand, that's also a good one. You'll see that thing is then, well, we'll come to it. But those are things that they think of, they use, and those are things that I want to fit into the next, after the break, into the familiar harmonic oscillator, show you how all these phenomena take place on the circle. And then the lecture afterwards, we'll see how we can use the circle and our hyperbola for the discount and put it all together. And then you'll be running. Okay? All right. So let's take a short break. Now we'll reconvene at 5:15. So we had quite a good discussion in the break here about some details. And the first thing you always have to keep in mind, especially if you're a control engineer here, is that what we're talking about all the time is signals, okay? So if we do Laplace transform, nobody takes a Laplace transform of the energy. I mean, there are people who do, but what you do rather is take Laplace transforms of signals and then figure out what the Laplace transform of the energy will have to be. You'll have to do some convolution, or maybe the power spectral density or something like that, right? So that's something to always keep in mind, okay? So what does this controller do? Well, the controller does really two things. So first of all, it applies either a force or a velocity. So economically speaking, it either is coming with a want, a desire, right, a level of desirability, or a quantity demanded or a flow, right, depending on what analogy you're using, all right? That's what it decides. It can only decide one of the two. Okay, so if the ECB is changing the interest rate, and the interest rate is the price of money, then then it has a want. You know, it says, okay, I want to buy or sell, and this is how I'm changing my price, and this change of price is my want, right? This is what I want. Eh? But when it does that, it's not just so, and now guys sort it out. Now it has to be ready and able to deliver any quantity whatsoever at this new price. Okay, it can't just say, okay, now my job is done, and they do. So the banks will then borrow at the ECB or loan to the ECB at this rate, you know, and they can just use this rate and just dump everything they want or get as much as they want. Now the rates are negative, so the bank don't want to dump very much, but they want to get a lot, no problem, right? Negative rate, you know, super, huh? And our government, same thing. I mean, they're doing all the support of businesses during Corona, and there are negative rates. So this Minister of Finance, he said, well, yeah, we can borrow as much as we want. It's actually good business, sure. You just borrow money and they pay you, huh? So there's all these pension funds who are willing to pay in order to have the government use their money in order to support whoever suffers from the consequences of the corona measures, right? But the important point is when you control something in economics as in engineering, you either set a force or a flow, so either a want or a quantity demanded, right? Either some demand or your wants or a willingness, if you integrate that a little bit. And then the other variable, you got to be ready to do whatever it takes, okay? Now, the other variable, you don't even know what the sign is going to be. So the ECB actually, or the Federal Reserve, I don't know about the ECB, excuse me. During the crisis of 2008, they spent a lot of money, all right? So there was a credit crisis, so nobody wanted to extend credit, and they started to extend credit, okay, at very low rates. And the rates were very high. So, I mean, it was a party for a lot of people who got saved, by the way, on this. But then the market started picking up, and then they were able to get rid of quite a bit of it, you know, now. I don't know how much. They never published this, okay? And I don't look very much because I'm probably not going to like what I'm going to see. But they got rid of it, and then they made a profit again. So you see, even the direction of the power flow, you don't really know. It can be positive here and negative there, and then turn around, right? So first you have to decide what's positive and what's negative, because that's not given. But if the effort and the flow on a bond have the same sign, then it's going to be positive, and it can flip around. You know, you don't know. You know, like if you put a battery on a motor, an electromotor. You know, we do that nowadays in these hybrid cars. A normal operation with old cars, you would think, look, the power is always going from the battery to the motor. You know, huh? You know, well, why? But nowadays, they turn it the other way around. All of a sudden, they use the braking action to start turning that thing into a generator, and they push it right back in, all right? So you just don't know. So you can say, well, I have a supply line, and it's obviously going this way, but maybe they're restocking, it's going the other way. And if you build a linear system, there's nowhere there to be able to prevent that, in principle, from happening. It's a linear system, after all. So both the economic force, the want, and the quantity can just go negative. I mean, every which way. All right? Huh? You want to prevent it, you have to put in nonlinear systems, you know, like a diode or so. You say, okay, no restocking, and you effectively put a diode in there. Okay, so yes, so this is probably good to really bear in mind, because economists are quite confused about when they say cash flow or growth or activity, what it is they really mean. All right, and all you have to work with are signals, either a force or a velocity or a voltage or this. Okay, and then the rest has to follow. Now, even in systems theory, you've got to be careful. You can't just, you know, take two blocks and I have one transfer function here and another there, right? And then just say, hey, the total thing is the product, right? That doesn't work very, right? You've got to have some humongous impedance here in order to make that work. Otherwise, you're not allowed to do that. And they do that. They do this impedance matching. So they make one impedance really, really high so that this thing doesn't take much power from there. Otherwise, it's not going to work. You know, you can't multiply it out. It gets more complicated. You'll have to make a bond graph and see.
I thought that we did this all the time.
I know, but the assumption is that there is no significant power transfer. You do it all the time, but, you know, be careful.
They're just talking about a block diagram.
Yes, yes. You can only multiply if you have a very high impedance, okay, on the other side. So there is no, look it up, and then we're going to talk more about this, right? But in preparation of that lecture, look it up, because otherwise we'll get distracted, right? You can't just multiply. We do it all the time, but we need to be careful, and we're not careful all the time, right, as engineers, huh? As you know. You know the old joke. You know the old joke, the physicist, the mathematician, and the engineer, huh? You know that one, huh?
There's quite a few.
So they're proving this theorem that all odd numbers are prime numbers, right? So the mathematician, he goes first 1's prime, 3's prime, 5's prime, 7 primes, 9's not prime, false, right? The physicist, 1's prime, 3's prime, 5's prime, 7 prime, 9 not prime, measurement error, 11 prime, 13 prime, theorem approximately true, right? Now comes the engineer. He's not very careful. 1's prime, 3's prime, 5's prime, 7 prime, 9 prime, 11, always true, right? Huh? So we have a reputation for not being too careful, huh? Which is good, because we're the only ones who get anything done, right? But sometimes we make big mistakes. Okay. So, so much for that. So I think that was a question of yours and a question of yours, right? So make an important distinction between signals and energy, right? Which, this is part of this whole fitting process here. I mean, this problem is why I like bond graphs, you know. There's a lot of problems with just working with signals, you know. A lot of problems. Now, what I want to do is, with the remaining time, be very specific about two cases, okay? So what we want to do now is that all these deliberations we had before, we want to get them in the form of a circle, right? So we know that when we can wrap a signal around the circle, we are doing a Fourier transform. So the second order system is the first system where we can get frequencies. So here I plotted one. And these are phase portraits, okay? So this is your stock, and this is the price level, all right? And what I try to do here is an entire economy and use the words that they would use, okay? So think of this as a harmonic oscillator. There's no damping, you know, so pure Fourier transforms, all right? Or, no, let's leave it simple, right? Huh? And this will just be momentum, and this will be position, and you'll get, and then you rescale it a little bit, otherwise you'll see an ellipse where you just get the circle, right? So the thing, it buzzes around like this in the phase plane. That's just what we call the Hamiltonian flow, all right? Now, what's going on here? Okay, now this whole thing, there's a lot of words, and if you read all these things, you will see that, I mean, there's articles and books. And what I find stunning is that with this little bit of insight from economic engineering, we can all put it into one picture, okay? And I have a similar picture for a business here and the banking cycle. So those are the two pictures I want to step through. And they're, of course, tentative, right? I mean, none of this is necessarily super true or super false, but it's a way you can very explicitly think about an economy. So what they'll have, you know, is they'll have this expansion, boom, recession, depression. This is the color codes, right? Okay? So fast forward to here, same color coding, all right? So there's a boom, prices are high, you know? We're at the peak, everybody's running, and the system is moving. You have a huge increase in goods, okay? Huh? So It's a period of what they would call overproduction, right? Huh? Okay, so the zero velocity, that's like equilibrium production, okay? Huh? Then overproduction, so all this stuff has to go somewhere. So people are not consuming so much, so everybody's buying these iPhones, and at a certain point everybody's got them, okay? And the stuff is what we would call abundant, all right? But in order to find buyers, the price just keeps dropping. So you start already something on what they would call a downswing, and it's usually a drop in prices, okay? So from this peak here to the trough, you'll see what they would call as a downswing. And here I've mapped it as a downswing in prices, okay? So you can, and that's not so bad because look, before we thought of it as a kinetic energy, and you know, that is maybe with the square, but that doesn't, the square doesn't really change the topology of the circle very much, okay? So it's at least approximately true, huh? Okay? So then what they do is after the green comes the orange, so I put it in there, this is what they will call a recession. So prices are dropping, and then prices are really low, and this is what they would call a depression, all right? Everything becomes cheap, and this is the expensive side, right? And this is neutral here, okay? But now, rather than overproduction, I have, this is wrong, because I was cutting and pasting quite a bit. You get
Overconsumption or
overconsumption, yeah. So this is underconsumption, right? Huh? Yeah, this is underconsumption. This should be under production, huh? Production, huh?
I mean, underconsumption or overproduction are basically the same thing. I mean, they're
That's right. So these should be the same,
yeah.
right? The reason I should really have called this, I got a little bit confused because I had, stupid me, I put the phase portrait as turning the wrong way around. So I wanted to correct that before I did this. I mean, it would have been, I would have been corrected by Koen, and then some of the cutting and pasting didn't work out right. So, but that's okay, because this is really under consumption. And there's a reason I put it in there, consumption. This is kind of the most important thing. This is Keynes's idea of why recessions start. They say there's not enough consumption, all right? So we need to stimulate consumption. So the word underconsumption is more important than overproduction, but it somehow feels more natural to say overproduction, okay? And here you get underproduction, and which is also a way economists say, well, you got a problem here, right? So demand is picking up, but businesses haven't invested yet. They don't have to start up. We have underproduction, right? Huh? So prices start moving very fast up because the things are not being produced, okay? So the irony is a lot of these things get analyzed from the so this is really overconsumption, but nobody talks of it like that. They all think of the problem rather than the solution, you know? Okay? But you see, it doesn't matter. It's all the same, huh? Yeah, so they'll talk about this. So this messed up a little bit, right? Okay? So in the Depression, all the business, you know, you see the signs, you know, closed and with some cobwebs on the gate and no workers going in, etc. All right? And then the goods become scarce, you know, rather than abundant. Okay? And prices keep going up. So you're on an upswing. Okay? And then all these businesses start cranking out new stuff. You come in the boom, it's overproduction, and you just keep going. All right? And the analogy that is used is that the Q is called the availability of the goods. So very available, it means it's abundant, and not available at all, it means scarce. And scarcity is actually another extremely important concept in regular economics, okay? So what this suggests here is the, I always forget the names of it, but it's the electrical engineering analog, What is that? Is that the impedance or is that the admittance analog?
Impedance.
That's the impedance. That's the impedance analog. You're right. This is the impedance analog. So this Q is more of a charge, right? Not a level. Huh? It's not an inventory level. That's more for a business. This is a charge, you know, stuff that you have, availability, you know now. And this I called price level. So it's not an amount of credit, but it's the level of the prices. That's how economists will talk. So you will see this is all in the impedance analog. And everything in the impedance analog is best modeled with an electrical system rather than a mechanical system, right? So the capacitors are holding the availability of stuff, and the inductors are giving you the price level by just telling you what the magnetic flux is, the level of the magnetic field, really. Huh? So you see the magnetism becomes the price, the level of the intensity of the magnetism, right? Huh? And so, I mean, the thing is, this is what they call a trough, this is what they call a peak. I mean, I have a million other words, and you just kind of put it in. But I think this is to me, this is a very nice picture, and really tells you how economic engineering with a simple harmonic oscillator just clears up a lot of these terms that they would use. All right? I mean, how do you make sense out of this, right? Now you know. It is just the price level going up, but you could also call it the square of this, would be the kinetic energy, right? Huh? Okay. I want this to be under consumption. So I expected to spend at least 20 minutes talking about this, and apparently I did such a good job that I don't see there's anything more to say, right? Do you guys all agree? Huh? That's just what it is. Huh? So the only thing you need to realize after all of this is that this number is a complex number, right? But there's a minus sign because it's going in the other direction. And it's just scooting along like that, right? With this frequency. And this is omega n. Right? And you're done. You did your Fourier transform. Boom. All right? Of course, the Fourier transform of a harmonic oscillator is extremely non-interesting because it's just got this one point in the spectrum, right? But that's not the point. The point is, of course, when you build your own system, you're going to have, I don't know, 6, 7 harmonic oscillators, right? And they're all going to provide, points in the spectrum, okay? And you can just look at the Bode plot, and you will see, what thing you can try to mess with this economy, but you will see what the resonance frequencies are, what the lag and the lead is. Obviously, this is a lead indicator for this lag, and this is a lead for that lag, and I don't know. Okay. Let's go to businesses. It's a little bit less studied, and it's all the same, really. But this is you have the impedance analog and the admittance analog, right? For the regular Newtonian analog, right? This, I would say, is the admittance analog. So we think of momentum as something that you pour into something, right? And momentum is also an amount of credit per unit or something, right? But we can just look at some kind of standard unit, some standard capital that's in there, multiply it out, and this will be angular momentum, and this will be an angular velocity and all of that, right? Angular momentum, and then here would be the position, the angle, right? The angle of this thing. And then it takes a thing of credit. So credit to me is like something you hold, right? So it doesn't become a level, but something you store it in there. And then here is then the debt. And then this is sometimes also called the banking cycle. So you see, it's you can measure the contraction. They call it a contraction instead of recession. But they mean that the credit is contracting, right? So that all the, and here the amount of credit is expanding. The credit is contracting, prices are dropping, of course. Inventories are high. Instead of availability, you're talking inventory level, huh?
But then
Excess demand and excess.
yeah, switch around excess demand and excess supply.
Yeah, so it's kind of confusing here. So what I did is I thought of demand as coming from outside the system here, But you're right, you can probably better to call this supply, all right, for the business itself.
So it goes into the inventory.
Yeah, so the way I thought of this was that the business is delivering to the customers, okay? So the customers have then the inventories, you see, and they're exerting this high level of demand. So this is a little misleading here in the end. I think what you say is exactly right. If you take from the perspective of the business, it's exactly the other way around, right? So this would be supply, and this would be demand, and this will be long, and this will be short inventories, okay? This is from the perspective of the consumers. And the reason I did that is that the banking system, they kind of talk that way, okay? Was more the banking cycle. I wanted to make the connection with banks. They say, there's excess demand, or economists talk that way, right? So they flip the sign on everything, all right? They'll say inventory levels are, high, consumers have a lot, huh? So you're completely right, huh? This all depends on whose demand this is and whose inventories these are. Huh? Okay? And we won't talk about, but I think it would have been, in hindsight, a little bit better to do this as supply, and then keep this long, and do this demand, and then, So then they buy low, and then they sell high, the business, Okay? Yeah. Like these things, it's just a really good point, like there's so many different perspectives. You can look at traders on the futures markets, and then this will be contango, and this will be backwardation. You won't talk about an upswing or a downswing. When prices are rising, they call it contango. When prices are dropping, they call it backwardation. Everybody's got their name for it, And when they talk about inventories, they say the inventory is outside somewhere else, rather than in mine. Huh? So when you draw your analog here, I guess I'm using the question is, if you have a mass spring system, you put the spring here, or do you put it here, huh? For instance, if this is the positive direction, huh? But I think in hindsight, I think it will be better to call this supply, less confusing. But maybe it's good to be confused also, because it is, and then sort it out. Huh? So what do I want to achieve with this thing? Well, we can go pat ourselves on the back that we got an economy, but then I take a business, and thanks to you guys, you can just see what perspective you want to take from where is the positive sign, what's the negative sign, whose inventory is it, whose demand is it, and okay.
I don't know if it makes any sense, but shouldn't order parts be aligned with the axis? Because I'm thinking, if you look at a regression, for example,
Oh, you mean like this? Huh?
Yeah, so it should be basically, because in a regression.
45 degrees, you mean, right? Huh?
Yeah, because in a regression the growth is still positive, growth rate is negative.
Yeah, that's not how these guys think about it, right? So if you see here, for instance, huh?
Yeah, but I think if you, let's say if you draw a horizontal line in the middle, which is zero growth, for example, I think recession and the economy is still growing, but the growth rate is negative, so at some point it dips below zero and then you enter the depression, right? The growth is positive or negative and the rate is positive or negative, which gives you the 4 different options.
You know, it's a good point. I mean, I ended up opting for this, you know, because the boom is you're just like producing like a maniac. And here you can see the way the circle works. You have a rather flat area here where, you know, I don't think they know, okay? I think you can make a good point for either, you know? I ultimately settled on this, but, huh? I think it all depends on your definition, and nobody has a good definition of a recession. Some people say when, you know, yeah, some people look at the price level, you know, huh? So I looked at Wikipedia for this one, and I think also at the Britannica, that's what I kind of used, and then they would describe this like a sustained drop in the price level during a recession, right? Now, you can see that here, this little quarter gives you a big, you know, this speed is huge, right? Huh? And from 45 degrees is not changing that much anymore, right? It's really flattening out. And you have a sustained period of consumption. You see what I'm saying? So that's why I opted for this. But I don't want, you see my reasoning, huh? Because that's the way they would describe it. The sustained period where prices are dropping, or a sustained period where prices are rising, and then here a sustained period where their factories are producing, and here a underconsumption and a sustained period. Huh? So one of the most important things was underconsumption. So they look for a piece of the pie here where the underconsumption is the greatest, and definitely that will be in this quadrant. Giving you a little bit of a long answer because I don't think there is one good answer, you know. It just depends on what you're looking at. So by deciphering what they're saying, I kind of settled on this, you know. And that's how I also came with this silly thing that this is excess demand, because the guy just kept talking and talking about this, and then this was clear this was demand from two businesses, you know, so the business sees this demand and says, hey, there is excess demand, whereas what Koen is saying, yeah, this should, and Emil, this should be supply because the business is supplying, but for some reason they don't talk about it like that, right? So then I try to fit it in like that, but again, the same thing, don't get stuck on that. You know, now it's just the way I was trying to copy his reasoning and then put the terms into the, you know, all the movement on the circle, right, in the negative direction, which is all we're looking for. So yeah. You can slice this pizza the way you want, right? And you can name these things. Some people call it something else, you know. I don't know, they call this, what have I ever seen here? Yeah, I don't know, I can't even think. Huh? No, all kinds of different names. Now this is just one thing, you have all kinds of other markets, stock markets, they have cycles, you know, and low inventory, high inventory, overstock. I don't know how they do it, right? It all is going to depend on your application. This is just there to give some ideas on, well, how you got to do this. You start with your signals, and draw. If you know you got a you got an oscillation, you know you have a second order system. So just sweep over in a Bodhi plot, just sweep over the natural frequencies and try to find which one is in there. That's all you're doing, really. Huh? And then, because in the end, you can say, well, you still haven't done the Laplace transform, but maybe I should mention that here. If you have the Laplace transform, you get your signal. And so whatever this force is, and you do this, right? But this thing is e to the minus sigma t times e to the minus I omega t. So what you can do is saying, well, I'm really taking the Fourier transform of this signal This is how they define the Laplace transform. So you know what the Fourier transform is, and you say, well, I'll take whatever signal I have, I'll knock it down with this thing, and then that is my definition of the Laplace transform, all right? Huh? So what you can do in practice is you kind of detrend it like that, and then you start looking at what frequency is in there, okay? Next lecture, I want to do this the right way, you know, because just the trending with this sigma is not right, you know, because you never know whether there is a surplus or a deficit tied to the conjugacy, right? Huh? If you know what I mean, like if you have this complex conjugate pole, if you keep moving the poles, you will find that the true discount rate is right here, but you're only seeing the cosine of it, you know. Okay. All right. Any other comments on this? This is all pretty much open-ended stuff. Okay. Then I have 10 more minutes. I want to do my last thing. And this thing is not complete without kind of mentioning that the higher dimensions is the thing that worries most economists, especially Keynesian economists. So they don't just have one good like we have here, right? Or one type of capital and a price, and then they look at rotation of phase plane. So Keynes, he came up with this theory that there is at least two things going on, two Qs. There is an investment and there is a consumption, right? Huh? And both of these have prices, of course. And they interact with one another. So we have a two-dimensional harmonic oscillator. And they can interact with one another, and they can exchange energy if you had a harmonic oscillator. Of course they can, right? Huh? You can look at the modes, and then you have very special combinations that they don't do it, but normally you will see they will interact with each other. And these interactions have names. So the way investment works on consumption is what they call the multiplier, Keynesian multiplier. And the way consumption then influences investment is what is called the accelerator. And then they combine these two and they get a cycle. So they are not able to reason that they can get a cycle just in the investment or the consumption markets individually, because they don't have the concept of an inertia and a storage working in concert to create that on a single good, all right? So the theory is sort of roundabout. So they have to say that they have two first-order systems, and this one is influencing the other, and the other influencing the one, creating the business cycle. And that's the multiplier accelerator model of Keynes. Now, seems very roundabout, but it's very, very popular, you know, and it's like the de facto thing that most politicians would use, you know, when they do these type of analyses, okay? So they start looking at the multiplier and then the accelerator, okay? Now, I haven't done any analysis here, and I would say this is, you know, a really nice thesis, for instance, okay? But you'll see that rather than being on a circle, you're now a circle on a circle of circles, right? So if you have just one-dimensional system, you know how it looks. It's just, huh? But now you have a two-dimensional system, so you got two circles. So you got all combinations of one circle with another circle, okay? And what do you get when you have a circle of circles? Well, you have a circle, and you just make a circle of circles, right? And it's called a donut. All right?
Doors.
Huh?
Doors.
Or,
Official terms.
yeah, so if you're,
donut.
yeah, a donut, right? So, or if you're sophisticated like Koen is, you would call it a torus, right? Huh?
This American person.
Yeah. And he would know that the plural is tori. Huh? Huh? So, but you only have one. Huh? It's a torus. Huh? It's a manifold that has, I think this is a T2. Huh? T. Yep. Huh? So now this is a pretty nice system, but before we end this, you will see this is not a joke now, right? I mean, you can be lucky and you can see that these two rotations, they're compatible in the sense that if you divide one over the other, that they are a rational number at least, you know, 1 over 3 or something like that, okay? And then what happens is you can count the number of times you go over the, I wanted to say donut, but I'll say torus, over this one with respect to that circle. I mean, this is just the way it's drawn. That one is bigger than the other. You know, and then the thing will meet up again, right? Huh? But if they are not, if they're not compatible, so they're not an octave higher or this, they're not harmonics, you can get like weird issues, and the whole thing will fill up, and you get chaos. It's called chaos, right? So this simple thing is already, in mechanics, it can be a chaotic system because keeping these exactly synchronized is very hard. And you've all analyzed these with these Lissajous figures, I believe, right? Can you remember that? Only the physicist doesn't know. Huh?
I also know.
I only know that from Arnold, so I don't think we ever saw it actually.
No?
No.
Those Lissajous figures, you know?
No idea.
When you see a second order system, you know, now it makes these beautiful. When I did undergraduate, this is what they taught us and stuff, but obviously.
Yeah, no, we don't use it.
Sine signal on the x-axis, plot it over time, and the same over the y-axis. If they got the same frequency, it can be either a diagonal line or a circle.
Or
It's
then
like
or
you show
butterfly.
It's like twice as large. You get like a butterfly.
Yeah.
Telescopes.
Yeah.
Yeah.
Yeah, so you got these two harmonic oscillators. So you got Keynes's investment and consumption cycles, and they're interacting, right? Now, if they're harmonics of one another, things are going to be fine, right? So you're just playing piano or flute or no, well, flute you can only make one tone, right? So, so you're playing guitar or piano, but if they're not, you know.
Yeah, that's what makes something sound flat.
That's right.
It doesn't.
Yeah, it doesn't.
If it isn't harmonic.
Yeah, but these kind of systems are very hard to analyze. It's called chaotic systems and very hard to deal with. So, but anyway, what?
No.
Huh?
I was just thinking if you let the arrow just continue over time, then after some cycles, it might end up at the starting point again.
Only if it's rational,
Only if it's
right?
Yeah.
Otherwise, I mean, exactly, think about it. That means so many of these will fit in so many of these, right?
Yeah.
Eh? But suppose that ratio is not rational, it's irrational. Then that's saying it will never fit, so it's going to fill the entire phase space. Huh? Okay? It will never come back.
There are some instruments that are not entirely tuned. Because of that.
I see, yeah, but that problem. Yeah.
One of the most famous guitars cannot tune one string completely properly.
Depends on what key you're playing in.
No, it's really it has to do with the ratio with respect to the other strings.
Yeah.
So one of the interesting things that comes out of here in these modern theories is that a lot of physicists, you know, and we have a one right here, well, he's ex-physicist, will argue that this is the origin of the notion of entropy, right? So in this system, you can imagine that if you can measure what this stuff is, you know it's going to come back and you're okay, right? So, of course, if you can measure infinitely finely, you always know where it is. But they have something the physicists will call coarse graining, and they will say you're never able to measure both momentum and position. So you'll never be able to measure both price and quantity in economics. So that's the case in the Netherlands, because if you're paying cash, you can't pay for less than 5 cents, and if you pay by transfers, it's not less than a penny, right? So if the price is somewhere between, you're never going to get exactly right, you know? And you can't buy 1/1,000,000th of a slice of bread, and you know, you got problems. So you're always going to, you know, like have a little patch here. Now, because this thing is quite regularly, it doesn't really matter, right? So you got this patch going on, and you can keep track where the system is. But this guy, you got a serious problem if you are not able to measure infinitely finely in the phase plane, right? Okay, so at a certain point, these things are coming quite close, and you're sitting there with your measurement of what price and quantity is, P and Q. So you don't know where you are, right? So this thing is starting to spread out. And after a while, all you know, it's somewhere uniformly distributed on this torus, you know? You don't know how long ago, you'll just go, I don't know anymore. Here you'll know it'd be somewhere on this submanifold here. Maybe I didn't know the initial conditions. So, and that change from a distinction that starts out to where it is exactly that you know that, to where you let it go for a little bit, you have no idea anymore. That is what is a source of what's called entropy, okay? So you lose track of where your energy is. So if you look in the phase plane, your energy is always going to be on this little circle here. That's your Hamiltonian. That's your economic surplus. But here it can be anywhere, all right? And that losing track where your money is, that's is the notion of entropy, right? So, of course, in earlier things, considerations of entropy, I'd say, well, it leaks into other degrees of freedom, and that can happen too. But even if you have only a 2-degree of freedom system, you can lose information like this. You can have entropy develop. And that's the same in economics. So the Keynesian approach is often advertised as being the path to infinite welfare. So you just put the money in, everybody will multiply and accelerate, and then everybody be happy, and you just have more welfare and more money, right? Now that's right, as long as the government can keep track of exactly where this thing is and then can pull it out again, right? But they can't, all right? So at a certain point, this is what the economic engineering analog will predict, is that the money is all spread out. It's all over the place. You don't know how to find it anymore. It's gone. And then the government achieved nothing, right? Sure, in the beginning, there's a lot of activity, and then it all dies down. And then everybody's just got a pile of debt, okay? All right? That's what this theory will predict. But I'll leave you with this, all right? And then next semester, we're going to put everything together and do the little bit of math, all right? A little bit of math, yeah, a little bit. Just a bit of Riemann sphering. Okay? Thank you very much. And then I'll see you guys, well, either in a meeting or on Thursday, all right? Okay.
Mag ik nog een vraagje over